My name is Stephanie Pullan. I'm at Cranfield University and the title of my project is Pesticide Fate Modelling at the Catchment Scale. We'll start with the pesticides. They're used as a plant protection product on arable as well as other sources. So you can also put it on railways, in golf courses, on forestry, but 80% of all applications in the UK are on arable or horticulture. So it's quite a large percentage. And what happens is basically when you put them on the land, they end up in water resources. So what that means for drinking water quality is that when you put pesticides in water resources, water companies have to provide water to the consumer. It needs to be above 0.1 micrograms per litre at the taps. That's 1 part per billion with pesticides or for an individual pesticide. So what happens is they have to treat the water that comes in for their raw water resource. And that means that they have to either spend a lot of money treating it. Some sites don't have treatment. Some can deal with background concentrations but not peak concentrations. And some sites, pesticides are really difficult to remove. So chlorpyrrolide and metaldehyde are really good examples of this where they can't actually remove it. So we're trying to look at, to develop a model. So trying to look at how to create how the pesticide's going on, what happens in the soil to it. So does it get degraded? Does it like being in the water, or does it like attaching to the soil particles? And then when it rains, how does it then get out of the soil and into the water resource? And if we can model those pathways, we can look at potential management of what we can put in, or the water company can look at working with farmers. You know, in the case of metaldehyde, they could encourage a movement towards ferric phosphate. So metaldehyde is used in slug control. So one water company's looked at actually paying farmers to use ferric phosphate, which is a different kind of pesticide, but they can treat and they don't have as many problems with. So it all stems from something called a soil-water balance. So I'm looking at what goes into the soil in terms of rainfall and what kind of comes out of the soil, so the different pathways that water leaves the soil, and whether those pathways are carrying pesticides with them. I enjoy the model working. So when you get that model run and it actually works, often you get with modelling is that you get little errors in the code. So suddenly you'll change catchments. So you'll move from one catchment to another. There's a different set of soil types. And then suddenly your model will be like, sorry, you've got to divide by 0 somewhere. And you're like, oh, it's so frustrating. But when it works and you get results and you can actually look at your modelled results against the observed data, and you can see that you're reproducing your results, it's a really good feeling of being like, this is what I've done. I've created this. That's really good. Soil's important for everything, basically. It's important for food production. It's important for drinking water quality. It's important for diversity within the ecosystem services. So it provides so much, but people just see it as soil. So they always look at like the end product. So like, oh, we've got a good yield. We've got good drinking water. We've got water in the catchment. But they forget that, you know, the soil is the main driver behind that. It's so important, but people just, because it's just there under our feet and it's there all the time, that you don't really notice it and you don't really appreciate its worth. And it's really important to get out there that, yeah, soil's really important for everything, basically. I'd really like to be able to communicate my science to like the younger generation. So I feel that the curriculum can sometimes be a bit restrictive in what they teach, and I think that sometimes they need to have more space for outside people to come in and I know a lot of the BS Cubed Act themselves do a lot of work with promoting soils to children. I think that's such an important thing, because if you can pass your science on to the younger generation and you can teach them when they're younger, not just a curriculum, but a little bit like, you know, about why water's important, why soil's important, why we need to conserve it. And if we can teach it and explain it when they're younger, and, you know, they can take that through, and then they're the people who are going to be making the decisions in the future. And if we can teach it to them and we can express our science to them, you know, then I think that's such a good thing. And I think it's really, really important. And that's what I'd hope that I could convey my science to the younger generation as well, and they could be like, oh, that's really interesting, that's really cool, you know, I never thought about that, I didn't know about that, and then they then think about that a bit more, and then maybe it influences what they do themselves when they grow up.